In 1915, a British engineer named William Mills patented a small mechanical sequence, a pin, a lever, a spring-loaded striker that could arm a grenade in roughly a tenth of a second. Over a century later, the M67 still issued to soldiers today runs on that same fundamental layout. Every serious attempt to replace it has failed, and the reason has almost nothing to do with the pin. By the spring of 1915, British factories were working overtime to produce a new kind of weapon for the trenches, one that relied not on brute force but on a careful sequence of mechanical steps. William Mills, an engineer from Sunderland, had filed a patent that February for a compact grenade built around a simple idea. A steel pin holds a lever called the spoon, tight against the body. When the pin is pulled and the lever is released, a spring-loaded striker pivots forward, striking a percussion cap and setting off a timed pyrotechnic delay. The original Mills bomb, as it became known, featured a segmented cast-iron shell and a nickel-plated steel pin. Its 7-second delay was specified in the Ministry of Munitions Specification A340, long enough for a soldier to throw, but short enough to limit the enemy's reaction. The War Office's Ordnance Committee quickly recognized the advantage. In late 1915, they adopted the Mills No. 5 as the standard grenade for the British Expeditionary Force, citing its safety in handling and ease of mass production. By the end of the war, British factories had produced 76 million Mills bombs, a scale that dwarfed earlier grenade efforts. The design's appeal was not just in its lethality, but in its reliability and simplicity. The safety pin only blocked the lever, it did not restrain the striker spring directly. This meant that the grenade could be carried safely, yet armed in a single, deliberate motion. When the United States entered the conflict in 1917, a delegation from the US Ordnance Department traveled to Britain to study the Mills system firsthand. They returned with technical drawings and a clear mandate to replicate the pin and spoon mechanism for American production. The resulting Mark II grenade, introduced in 1918, kept the mechanical sequence almost unchanged. The main difference was a pinecone-style segmented body, cast to suit American foundries, and a steel core exploder to meet US explosive standards. The essential fuse layout, pin, lever, striker, delay, and detonator remained intact. It was a design already moving beyond British trenches, setting the groundwork for a global standard that would endure for generations. In 1939, the Soviet Armaments Board made a decisive move. Engineers led by A.V. Mishin studied captured British and American grenades and found the pin and spoon mechanism both familiar and efficient. Soviet records from that year show a direct order. The new F-1 grenade would feature a steel alloy body and a British-style fuse, dropping the wooden handle of earlier Russian designs. This was not just about engineering. Soviet factories were already set up for steel casting, not complex machining or aluminum work. And using a public domain design let them equip millions of soldiers quickly, sidestepping licensing fees and lengthy development cycles. The German path diverged sharply. The Wehrmacht's steel hand granate, or stick grenade, used a friction pull-cord fuse. To arm it, soldiers had to unscrew a cap, pull a cord to ignite a delay, then throw. The stick gave extra throwing distance, but the cord system brought its own hazards. Reports from the field noted that the friction igniter could fail if the cord snapped, got wet, or froze in harsh winters. Unlike the pin and spoon, there was no lever to restrain the striker, just the hope the cord would not snag or break. German manuals warned about timing the pull, and Allied intelligence after the war listed more misfires and accidental detonations compared to the Mills system. By the start of World War II, these choices shaped the battlefield. The Soviet F-1's pin and spoon offered reliable, repeatable steps, while the German stick grenade depended on a fragile sequence. The Mills patent's public domain status and mechanical reliability cemented its place as the standard for mass armies, while alternatives faded. Popular culture often gets the basics of hand grenade operation wrong. The image of a soldier yanking a pin and tossing the grenade as an unstoppable timer starts is familiar, but the mechanical reality is more nuanced and safer than most people realize. The heart of the system is a precise sequence of linked actions, each designed to prevent accidental detonation and allow for deliberate control in the field. The process begins with the safety pin. This steel pin threads through the lever, known as the spoon, and the body of the fuse. Its sole job is to block the lever from moving, not to restrain the striker spring directly. As long as the pin is in place, the grenade cannot arm, no matter how much it is jostled. Pulling the pin does not start the fuse, it simply makes arming possible. The lever, held tight by the user's grip, is the true gatekeeper. When the pin is removed and the lever is released, a spring inside the fuse snaps the lever outward. This action frees the striker, a small steel spindle under tension from its own spring. Within about 1/10 of a second, the striker pivots and strikes a percussion cap, igniting a pyrotechnic delay element. In the M67 grenade, the delay is engineered to burn for 4 to 5 seconds, long enough for a safe throw, short enough to deny the enemy a chance to throw it back. Field manuals confirm this timing, but real-world conditions can introduce variability. A crucial safety feature is the ability to reinsert the pin if the lever remains firmly held. If a throw is aborted or a soldier hesitates, the grenade can be rendered safe again, provided the striker has not moved. This dual-action mechanism, pin plus lever, forms a chain of 6 steps: pin removal, lever retention, lever release, striker action, delay ignition, and final detonation. Each stage is mechanically independent until the precise moment the striker fires. This engineering, refined since 1915, is the reason why the pin and spoon system remains the backbone of modern grenades, including the M67, still standard issue in 2026. Alaska's Cold Regions Test Center logged a series of unexpected results in the early 2000s. M67 grenades exposed to minus 20 degrees Celsius for hours routinely clocked delay times well above the standard. Some fuses burned for more than 6 seconds before detonation. That extra second may sound trivial, but in live fire drills it forced instructors to rethink safe distances and timing. Temperature was not the only variable. Humidity and age also played a role. Old stockpiles, especially those stored in damp conditions, sometimes produced the opposite problem. A handful of training accidents in the 1990s traced back to grenades that detonated in less than 3 seconds, well under the minimum safety margin. Army Safety Center reports from that decade document 3 fatal incidents and several non-fatal injuries directly linked to short fuse batches. Each case involved grenades that left almost no time between the throw and the blast, far less than the manuals promised. To manage this uncertainty, soldiers learned to cook off a grenade, holding it for 2 or 3 seconds after releasing the lever, counting off before throwing. The idea was to ensure the delay had started, reducing the risk of a premature explosion in the hand. But this tactic came with its own risk. If the delay ran long, as in those cold weather tests, a cooked-off grenade could land and roll before detonating, putting friendly troops in danger. Manuals warned that the margin for error shrank dramatically when delay times drifted from the factory spec. Attempts to fix these problems with electronic or impact fuses have yet to fully replace the old system. Electronic grenades like the ETMP offer programmable delays, but at more than double the cost of an M67, and with added logistical headaches, batteries, circuitry, and field diagnostics. Impact-initiated grenades, while promising instant action, have shown reliability issues in extreme cold and on soft ground. The enduring appeal of the pin and spoon design, despite its quirks, comes down to a balance of cost, simplicity, and a century's worth of adaptation to real-world hazards. Programmers of modern ordnance have long promised a leap beyond the old mechanical fuse. The enhanced tactical multi-purpose grenade, called ETMP, arrived with a sealed battery, a microcontroller, and selectable fragmentation modes. On paper, it offers a programmable delay, 2.5 seconds or 5 seconds at the flick of a switch, and a built-in self-destruct feature. But the sticker price is hard to ignore, over $100 per grenade, more than twice the cost of an M67. Field trials flagged further issues. The ETMP's electronics required new diagnostic tools and a separate battery supply chain, complicating logistics for units accustomed to mechanical spares. Meanwhile, Russia's RGO and RGN grenades tried to solve timing uncertainty with impact fuses. NATO reliability reports logged up to 9% failure rates on oblique impacts and occasional premature detonations during rough transport. Procurement memos consistently circle back to the same point. When faced with cost, supply, and reliability data, the supposed advantages of new tech rarely outweigh the proven, predictable mechanics of the pin-and-spoon system. Every grenade designer faces a stubborn physical reality. Fragments never behave as neatly as the blueprints suggest. The classic notched coil inside the M67, intended to break apart in even pieces, instead produces a spray that's chaotic. Some fragments spin far, others drop short, and a few may ricochet unpredictably. Controlled fragmentation studies from the US Ballistics Research Laboratory to British ordnance tests have shown that only a fraction of the fragments follow the intended radial paths. This unpredictability means that the promise of a perfectly uniform danger zone is a myth. In practice, soldiers and engineers accept this uncertainty, relying on the old pin-and-spoon fuse because, despite its quirks, it offers a pragmatic compromise, a known sequence, a familiar risk, and no surprises that can't be managed through training and experience. The pin and lever system endures, not because it is flawless, but because no alternative matches its balance of reliability, simplicity, and field control. In 2026, the M67 design still defines the battlefield. Sometimes the real story is not innovation, but the stubborn persistence of what actually works. Question the myths.